Well, thank you, Venkat. Thank you all for inviting me. I'm really excited to be here. And as Venkat had mentioned, I'm currently a postdoc at MIT. Next year, I'll be at Cornell. But today, I'll be talking about a topic that is with neither of those affiliations. I'm going to talk about my PhD work at Princeton, where I graduated from last year, about specific ion effects in aqueous electrolyte solutions from first principles derived machine learning potentials. Okay, so there's a lot of interest in modeling aqueous electrolyte solutions using molecular simulations because of their fundamental relevance to really a huge array of very important natural and industrial systems. One example is in biological systems where you have water and ions that play a very important role in stabilizing proteins and activating conformations for their biological activity. And there's a lot of challenges in modeling these systems from a molecular simulations perspective. And those challenges are largely based on the models used in those studies. So for example, proteins, systems consist of tens of thousands of atoms, which means the model needs to be very computationally efficient. And at the surface of these proteins, there are important short-range interactions like charge transfer and hydrogen bonding that controls the stability and reactivity of these structures. So you need chemical reactions that can catalyze by enzymes. So the model needs to be able to represent these kind of reactions and behaviors. And lastly, the stability and solubility of proteins in aqueous solvents is determined by specific ion species present. So we need models to be able to represent these specific ion effects. And what I mean by this is that some species of ions can cause proteins to solvate and solve into solution, while other species of ions will cause proteins to precipitate out of solution. And it turns out there's this very specific ordering or this ranking of ions that's known as this Hofmeister series. And it manifests in a lot of different electrolyte solution properties, for example, surface tension and activity coefficient. And the idea behind this very particular ranking is based on the ion species' ability to structure water around them. So on one end of the spectrum, there are these structure-making ions, or these kosmotropes, which are ions that have a high degree of hydration. They structure the water around them very tightly. And these types of ions are typically smaller. They have higher charge density. And on the other side, you have these structure-breaking ions, or ions that are chaotropes, which they have more loosely packed hydration shells. And these water structural behaviors are directly tied to dynamics. So kosmotropes have waters that are these, strongly bound to them, so the waters get slowed down. The opposite is true for chaotropes, where without the structuring effect, water is able to move much faster. So back to the challenge of modeling these aqueous electrolyte solutions properly, we really need to be able to represent the proper degrees of hydration structure on the molecular level. And one way to probe that is to represent the dynamics of water on a macroscopic level. So generally, we can think about doing this using classical force fields to probe the dynamics, like your Lennard-Jones, Coulombic interactions. The simplicity of these models allows us to access very large length and time scales. They're very cheap, but because of these parameters are generally fit to some specific system, usually they're not very transferable to other systems, and it's also making a lot of approximations about the true physics of the system. In particular, short-range interactions that can be very complex and difficult to represent with only a handful of parameters in this functional form. So we really sacrifice some chemical detail and transferability with this approach. So if we're actually to do this using these conventional force fields to study the water dynamics in the presence of ions, what we see is that they really fall short in a lot of ways. So experimentally, some ions will actually speed up waters up. Some ions will slow down water, but the empirical force fields say that they all get slowed down when you have, like every species of ion will slow down water. So something clearly is awry with these empirical force fields. We've actually extended areas of the study ourselves to show that these force fields, even when you include polarizability or scale charge phenomena, you still can't really represent the true physics of the system. So here I'm showing what's known as the Jones-Dole relationship, where the slope of this line you can think of as the strength of hydration or strength of structuring ability of an ion. So the black line is experiment, and so we can see even if you add polarizability effects, we still kind of overstructure water around these ions. So even kind of incorporating these effects, we still fall short in a lot of ways. So now we can kind of go back to the drawing board and think about how else can we represent these interactions better. So one way is to use directly quantum mechanical descriptions, fundamentally representing all the electrons in order to derive on-the-fly forces to obtain a simulation trajectory. Everything is explicitly represented, shifting dipoles free to move around in response to the environment. Also allows us to study chemically reactive systems, but these are very expensive and generally limited to very small length and time scales due to costs, and it's difficult for us to study large-scale thermodynamic properties, dynamic properties using this approach. And really in the last few years, or 10 years really, there's been something, I would say, like of a revolution in this area of model development and molecular simulations, where machine learning has been applied to the development of models as a way to avoid this accuracy versus computational cost trade-off. So these machine learning potentials can accurately represent chemical representations of quantum mechanical calculations while still being able to sample large length and time scales like empirical force fields, and then be able to study these thermodynamic properties from a first principles perspective. And I know I'm kind of preaching to the choir here. Lots of the seminal work in this area has been done by the folks of the center. But just to give more background, how you generally develop these models is by sampling the configurational phase space of a system of interest, and label these configurations with their corresponding quantum mechanical energies and forces, and then mapping these two things with each other with a neural network. And so when we use this model in simulation, this potential will recognize some complex pattern in the atomic environment, and it'll assign an atomic energy contribution to that particular pattern, and from that construct forces that drive the simulation. So essentially it's a way for us to perform these first principles derived simulations in a much faster and more efficient manner. And that can open up a lot of doors to study chemical systems and fluid phase phenomenon, and particularly electrolyte solutions. So there's a lot of different of these machine learning potentials frameworks out there today. I will just kind of particularly highlight one framework called the Deep Potential Molecular Dynamics framework, which is developed at Princeton by Ellen von Jong, Roberto Carwian, and many others. This is the framework that we're going to use in this study, and an important aspect of it is that we can achieve simulation speeds that scale linearly with system size, which is significantly improved from quantum mechanical methods, which DFT scales cubically, and other methods are even higher. And I want to point out a few of the, I think, very distinguished features of DPMD. There's this an active learning procedure framework associated, which allows us to do an iterative approach of learning the parameters of our neural network while exploring thermodynamic phase space in an efficient manner and minimize expensive quantum mechanical calculations needed for training. There's also been a significant amount of effort put towards the computational efficient implementation of DPMD on GPUs, and particularly massively parallel GPU platforms. For example, there was a recent work using DPMD to put 100 million atoms on Summit, a supercomputer at Oak Ridge National Lab. They won the Gordon Bell Prize for this effort in 2020. Okay, so we'll use this DPMD framework to study the problem that we want to tackle with electrolyte solutions. I do want to point out that these machine learning potentials are not necessarily silver bullets. We need to be careful about really exploring limitations of these model constructions to be able to concretely trust the model predictions. And one fundamental shortcoming of many of these machine learning potentials, including DPMD, is the limitation of these interactions within some localized atom-centered spherical representation with some predefined radial cutoff radius. So when you fit the total energy of a given configuration, that model is fit to the total energy, which includes the long-range interactions. But the central atom can only see atoms within some cutoff radius. So any long-range interaction that's present in the training data is actually kind of fit into the short-range region. So it incorporates this long-range part almost in a mean field way because there's no explicit interactions past the cutoff. And when you kind of throw this long-range part into the short-range fitting, not only does it not have any long-range interactions, but the short-range part is actually contaminated because you have this long-range portion incorporated. So that overall lowers the fitting accuracy. And so this nearsighted approach is really a point of concern from a physical perspective because there's a lot of studies that show the importance of long-range interactions for charged systems, polarized systems, generally heterogeneous systems, particularly for electrolyte solution systems, which we want to study because ion-ion interactions are very, very long-ranged. But there's also a lot of cases where you can get away with this local representation. And it remains somewhat of an open question what kind of circumstances we actually do need these explicit long-range interactions. So we developed a framework to kind of study this exact question. In what cases do you need explicit long-range interactions, and what cases can you get away with not? So we actually chose to implement this long-range interaction framework using this decomposition framework, where we take our total energy and we split it up into two pieces. The first is a pairwise electrostatic interaction, which we assign charges to all atoms, and these extend to infinite distances. And then we subtract this from the total energy, and that leaves us with this non-electrostatic portion. So your polarization, induction, correlation, all the complex short-range interactions, and we throw this part to the neural network. So we take advantage of this multi-dimensional capacity of the neural network to fit the very complex local representations, while the classical pairwise electrostatics is separately induced, and that can be extended to infinite distances and solved with long-range solvers. So we're essentially building a machine learning potential that's also physically motivated. The long-range part, we know that is governed by classical physics, just Coulombic interactions, no need to reinvent the wheel there. But we applied the neural network for the hard part, which is the short-range, non-electrostatic part. And in this goal of studying, what is the role of long-range interactions, we are actually building a model just for the purpose of this study. We're just fitting it to a very simple reference SPC classical model, just because it's a well-defined system and gives us a way to test the role of long-range interactions. And we'll fit to DFT and a little bit later I'll show. So we've trained two models, just a finite range model, which we denote as FR, and a long-range model, which we denote as LR. And basically just tried lots of different properties and see if we have any difference between these two models when we compare to the reference original SPC model that we fit to. So here I'm just showing one of these properties, just a dimer scan of just energy as you pull apart two waters isolated. And we see that the long-range model fits really well with the original SPC model, while the short-range model, not only does it not have long-range interactions past the cutoff, which is 6 angstroms in this case, but the short-range part actually suffers in the fitting because of this contamination issue I mentioned earlier. And I think that's even more clear in this plot here. I'm showing the distribution of force errors with this finite range model and the long-range model, where the long-range model or the finite range model has this contamination issue where the long-range part is actually being fit into the short-range part. So we see just smaller errors for this long-range approach, where we remove the long-range Coulombic portions. So this is kind of, looking at just forces and looking at an isolated system, but what about in bulk? What about when we actually, what is an actual application of these models when we study electrolyte solutions? So I'll just kind of go through a few different properties that show that we can actually, in fact, get away with not having explicit long-range interactions for these electrostatic or for these electrolyte solution properties. So just first looking at this is, by the way, for a sodium chloride solution, for a range of concentrations. So this is looking at just liquid density. We can predict the liquid density pretty well with both the finite and long-range model. This potential PMF of different ion pairings, both the finite range model and long-range model, converge. So we don't really have any discrepancies there. We looked at structure, this looking at GFR between all the different pairings and looking at structure factor, all around really great fitting for all of these structural properties. We then looked at even dynamics, looking at the self-diffusion coefficient of water and each of the ions. And more or less, we see pretty good agreement, even without explicit long-range interactions. This finite range model, this blue line, really agrees well with the original SPC model and the long-range less contaminated model. And the same with viscosity. So really across the board with all the properties that we looked at, there really is not much of a discrepancy, even when we don't have explicit long-range treatment. So knowing this information, we can then construct these DPMD models for electrolyte solutions to really improve upon the predictions of empirical models that we were looking at earlier. And now we can know with confidence that we can do this with this finite range approach, where we don't have to explicitly include long-range electrostatic interactions. So we trained 4 different electrolyte solution models, NaCl, KCl, NaBr, and CsCl in water. And these ions span the range of the Hofmeister series and across the entire concentration range relevant for each of these ion species. So now, instead of the SPC-based reference for these DPMD models, we're going to train to a quantum mechanical system, which much more closely resembles a real system. In particular, we train on DFT using SCAN, the scan exchange correlation functional, which is particularly good for water and aqueous solutions. And we're interested in studying specific ion trends from these models in bulk. But first, we want to validate our model to build trust in future predictions and establish some baseline predictions quantitatively. So we first validated our model against quantum mechanical and experimental results. The first is comparing our DPMD model for the sodium chloride structure against an ab initio molecular dynamics simulation done by our collaborators. And we see pretty excellent agreement across the board for all of these interactions. We then assess the capabilities of our model to represent the experimental structure factor for sodium chloride and also the associated NaOH and HCl system as well. And really, the model does an excellent job of representing the experimental structure here. I don't show it here, but we also looked at the solution density, and the models do a good job there as well, up to pretty high concentrations. So now that we have a good model, I'd like to tell just very quickly 2 short stories about what we can learn from these models. The first is going back to the topic of solution dynamics. And I mentioned earlier in the talk, different species of electrolyte solutions have really vastly different behaviors on the dynamics of water. So looking at diffusion versus concentration, experimentally, what's supposed to happen is that some ions slow down water and some ions speed up water, and they do so in the order of the Hofmeister series. The empirical force fields say that all the ions slow down water, so clearly something is misrepresented here. So now what about our newly constructed DPMD potentials? So that's shown here in the solid line of this plot. The dotted lines are experiment. And we can clearly see that our models span the range of slowing down water and speeding up water and qualitatively following the Hofmeister series. So this ability to predict the qualitative specific ion effects on the concentration trends in solution dynamics represent a distinct and pretty important attribute of these DPMD scan potentials that really exceeds the capability of the empirical models, although there are certainly quantitative discrepancies here. But I think we're very excited that we can kind of achieve this both speeding up and slowing down range that is missed in these empirical force fields. So we're now working on thinking about what kind of representations is present in these DPMD potentials that is not present in these empirical force fields. So that's kind of some ongoing work in progress. The second short story I want to share is about the how ions are able to structure water in bulk solutions. So historically, there's been this belief that when you apply pressure to water and when you add some salt to water, it kind of has the same effect on how water is structured. In both cases, you kind of have water that condenses together a bit, just everything kind of squishes together a bit when you add salt and when you add pressure. And structurally, experimentally, and via simulation, they've shown that. But we're able to use these DPMD potentials, which has ab initio accuracy analysis to sample time scales and length scales that allows us to access structure factor. What we actually see is that the structuring effect is 2 different phenomena for when you add pressure versus when you add salt. When you add pressure, what happens is that all the waters kind of homogeneously condense together. Every water molecule homogeneously moves a little bit closer to the next one. But when you add salt, the phenomenon changes such that it's really only the first hydration shell of water around the ions that actually squeezes together. Everything else reactively kind of responds to that movement, but it's not a homogeneous shift where everything condenses together homogeneously. It's a bit more complex. So it's really the first hydration shell that is the most impactful thing in how a salt or salt ion will structure water versus when you add pressure. So this is just a short short story about how I think these DPMD potentials can be really impactful in studying different aspects of properties of electrolyte solutions. Okay, so with that, I'll wrap up. So we've been able to look at different Hofmeister specific ion trends using empirical force fields and show that quantitatively there's overstructuring of water and ions. but we've built these machine learning potentials that can be applied to condensed phase aqueous solutions. When we tested whether or not we need to incorporate Lagrange interactions in these potentials, and we can find that we actually, for these electrolyte solutions, bulk dynamical properties, we can get away with these finite range models. And then we've used these models to study specific ion trends and also how waters are structured around ions, to using the benefits of first principles derived model that can also access these very large length and time scales. And so I'd like to thank a lot of the folks that were involved in this work at Princeton, and the Panacea-Topoulos group at Princeton, and also the CSI DOE Center that I worked in. I'm now actually kind of extending some of the work of these electrolyte solutions in bulk to systems of confinement and hydrophobic interfaces in my postdoc work in the Kulik group at MIT and in another DOE center, Center for Enhanced Nanofluidic Transport. So I'm very grateful for all of these people that I've been able to work with. And with that, I'm happy to take any questions.